Okay, in this podcast, we're going to take a look at what effect temperature has on rate. And in that discussion, we're going to talk about activation energy and ways to lower activation energy, specifically using catalysts. Okay, as you would imagine, if you increase the temperature, you're going to increase the reaction rate. Okay, so here we have a little plot that has K in temperature, and K is dependent on temperature. So in a chemical reaction, bonds are broken and new bonds are formed. Now, it's a little bit of a misconception, but whenever bonds are broken, energy is required. And whenever bonds are formed, energy is released. It gets confusing because people hear others talk about chemicals storing energy, and that when you break those bonds, you release that energy. And in fact, that's not really the way it works. When you break those bonds, it requires energy to do so. If other bonds form, that will reduce the energy. Okay, so let's get that clear. All right, molecules can only react if they collide. Okay, only way it will happen. They can't just see each other, they actually physically collide. So before collision, you have two species, atom, molecule. They collide, and in the process of colliding, they actually form this, what you might call an intermediate. And after they collide, they break apart into their two new products. Okay. So this whole area of what's going on in here is what we're going to be addressing with this podcast. So the other thing we saw in that diagram is there's some minimum amount of energy that's required to get that reaction started. And we call that energy activation energy. And we give it the symbol E for energy, sub A for activation. Okay? Just like a golfer golfing, you need some energy to get that ball over the hump, and then it can move on to the tee. Okay? So a reaction can't start unless there's sufficient energy to get it started. So this is we're going to draw a typical diagram, but what we call a potential energy diagram. This would be potential energy on this side. This is reaction progress or time on the x-axis. Okay? So here we are looking at a reaction where we start with reactants. They require some amount of activation energy to get them going, and then we have products at the end. So what would this be, an exothermic or an endothermic reaction? Well, as you can see, the products have lower energy than the reactants, which means the energy was lost, so this is an exothermic process. And as we talked about in our thermo section, the difference between where the reactants start and the products come out is our change in enthalpy, right? And then this additional piece is the activation energy. Okay, but we don't count that activation energy in the change in enthalpy. So what happens here is that point in between where we have reactants and products, where the reactants have collided together, come together, and start the rearranging process before the products come out. Okay, and we call that the activated complex. Okay, so this is where the activated complex is, and we call this also sometimes the transition state. So let's say we have a reactant and a reactant A and a reactant B, and they come together and collide. And as they do that, they start to rearrange what's going on with electrons and sharing, and so we call this the activated complex. Now out of that, we end up with two products, both product C. So if you could imagine, here's a more complex reactant. We start with this reactant. There's some rearranging that occurs. Okay, we reach this activated complex and then end up at a new product down here. Okay, So it's this rearranging of the molecule as things go that causes this activated complex or the transition state. Okay? So we call this high point the transition state. The species present at the transition state is called the activated complex. And the energy barrier between the reactants and the activated complex is called the activation energy barrier. That's the barrier or the hump that the golfer needed to get over, right? It's the energy barrier we need to overcome in order to cause the reaction to start. So what happens here is we look at the effect of a catalyst. Okay, so what's happening is, this is called the Maxwell-Boltzmann distribution. If you take a sample of some molecule or atom or solution, what you'll find is that they don't all have the same speed, that there'll be some distribution of speed that has some with very low energy and some with higher energy, but most of them are this average energy, right? And as you increase the temperature, what you are doing is you are causing this skewing in this Maxwell-Boltzmann distribution, right? And if you can imagine, this dotted line indicates the minimum energy for a reaction. So at any temperature we have this wide distribution. As the temperature increases, the curve flattens and broadens. So at a higher temperature, there's a larger percentage of molecules that have enough energy. Here, when it was the lower temperature, we had just this blue area, which represents the number of particles that have enough energy. But as we raise the temperature and flatten this curve, now we have this whole area, blue and red together, which represents the number of particles that have enough energy, causing you to come over the curve. So we can define the fraction of the molecules, and don't worry about this equation, but it's related to the activation energy, R, which is the gas constant, and T, which is the Kelvin temperature. Okay? So as we get enough molecules higher in energy, the reaction rate increases. Okay? So without some catalyst, it requires this much energy. If we have a catalyst, it's going to require some lower amount of energy. So what a catalyst does is it lowers the amount of activation energy. And the other interesting thing about a catalyst is you add it, the start of the reaction, at the end of the reaction, it's still there, unaltered. Now Arrhenius came up with this equation that we can use to help us determine the effect temperature has on K, on the rate. Okay? And this is basically what it is. K is the rate constant, A is some frequency factor for collisions, EA is the activation energy, R is the gas constant, and in this case we always use 8.3145 joules per mole, and T is, of course, is the Kelvin temperature. Okay. Now most of the time when we determine the activation energy, we actually rearrange the equation and use this, and this actually shows up on your equation sheet that you will have on the AP exam. Again, this is also called the Arrhenius equation. And the nice thing about this, just like we've seen in other things in this unit, is it fits into the form of y equals mx plus b, where y is the log of k, the slope is the activation energy over r, x is 1 over t, and of course log of a would be my b. Okay, so if I plot my x, which is 1 over t, and my log of k is my y, I get a straight line. And that straight line has a slope of the negative of the energy of activation over R. Okay, so if I plot the data, log of K, 1 over T, find the slope of that line, I can calculate my activation energy. So let's try that. So let's say plotting the natural log of K versus the reciprocal of Kelvin temperature gives us a straight line with a slope of minus 2.19 times 10 to the fourth. What's the activation energy for the reaction? Okay, so slope we know is the negative of the activation energy over R. Okay, so the activation energy, so if we fill in our slope and we fill in our R, the activation energy comes out to be 182 kilojoules per mole. Pretty easy to do when I'm given the slope. Okay, the other way that this equation can be reorganized is to take the log of K1 over K2 is equal to the activation energy over R times 1 over the final temperature minus the initial temperature. So if I want to evaluate what happens to K at different temperatures or what happens to temperatures with different Ks, this is the equation that I would use. Okay? So this is very much like the equation that we were using with a little bit of manipulation. So let's say we want to know the rate constant at temperature equals 350 K. If we know that at 298 K, the rate constant is this, and the activation energy is this. Okay, so this is the equation that I'm going to use. I can rearrange it. I can change this log of K1 over K2 to log of K1 minus the log of K2. And this part of the reaction equation stays the same. Okay? I can plug in what I know and calculate. Right? So here's my log of K1, which is given to me here. I'm trying to find K2. My activation energy is 49.7 kilojoules per mole, but because my R is in joules per mole, I changed this to joules. So I took 49.7 times 10 to the third times of here 1 over the initial temperature, the temperature I'm looking for, minus the temperature that I have a known K for. So let's just plug this in. Alright, so let's first calculate this piece, and I'll just go through and calculate and make sure that we're all good. Alright, I'm going to clear that. And I tend to over parentheses stuff to make sure that I'm good with my order of operations. So I'm going to start with 49.7, second EE3. Make sure you're not using the caret. And if you need my explanation for why that won't work, I can show you a couple examples. Divide by 8.3145 equals this portion. I'm going to multiply that times, and I'm going to put in parentheses this, and within that I'm going to say 1 divide by 350, close parentheses, minus in parentheses 1 divide by 298 in parentheses. I close those parentheses and I get minus 2.98. Okay, let me see if I can shrink this a little bit. Oh, okay. Alright, so minus 2.9 is what we have here. I'm going to change that to a positive by multiplying it times a -1. Okay, and I'm going to subtract it. We'll add it to the -3.3. So plus a -3.33822 gives me 0.35806. Okay. So my log of K is equal to this number. Okay, now I don't know how to take this directly and do the next, so I have to write down the log of k, which is 0.35802. So now what I'm going to do is clear this, and what I'm going to do is to the anti-natural log of negative, whoops, 0.35802, enter, and I get 0.699. over seconds. Okay. So if I have an exothermic reaction, the energy of activation is here, leading me to my products, which would be at lower energy. Okay, so the activation energy is the minimum amount of energy. It doesn't matter whether it's an exothermic or an endothermic process. There's still some amount of energy. So here where I'm endothermic, I've got to put energy in. It's this whole distance is my activation energy, because I got to go from where I am to the activated complex. Okay? And if you remember, this it's just this distance here that's going to be my delta H. It would be this distance here that would be my delta H over this side. Okay. So let's see if we can answer these questions. So here I have 3 graphs, potential energy diagrams, showing what's required for activation energy. So rank their reaction from slowest to fastest, assuming that they have nearly the same frequency factors. Okay. So let's take a look. So what effect is this activation energy going to have on my rate? It's going to have a pretty big one, right? So what I want to do is look at what it's going to take for me to get over the hump. Here it's going to take 15 kilojoules. Here it's going to take 25 kilojoules. And here it's going to take 20. So this should be the fastest, and this should be the slowest. Let's see. So the lower the activation energy, the faster the reaction. Hence the order is 2 is the slowest, 3 is the second slowest, and 1 is the fastest. Okay. What if we looked at the reverse reaction? Okay, let's rank those. So let's see. I have to go from here to here. That's going to take 25 here. Here I've got to go from down here. This would be my reactants. This would be my product. It's going to take 40 kilojoules. And here, my reactants are here, and I need to get up to here. That's only going to be 20. Okay. So this is going to take the most energy. It's going to be the slowest. This would take the second most, 25, and this would take the least. This is not sure how they, which is 20 if it's this or this, but it's probably 15 is what I'm looking at here. Okay. Okay, because the energy of activation, 2 is going to be the slowest, and 3 will be the fastest. Okay, so that makes sense. Okay, we're going to stop there.